All right, hey everyone. Just gonna wait for a while to make sure the audio is working. I just heard a massive bang as I stood up, so it does seem to be working. Okay, cool. Yeah, so today we're going to go through the second half of Math3711 or 5706. Last week we talked all about groups. So we talked about an introduction to group theory. We also talked about some direct products and sums, and also about abelian groups and the structure of finite abelian groups. But today we're going to talk about a second type of structure and a third type of structure called rings and fields. But they're essentially just an extension of groups. So not too much we haven't seen before. All right, so for example, a ring. Well, what's a ring? It's also a set, right? It's a set, and it has addition as well. So like an abelian group, it has addition, which means we have all the conditions of a group, and also it's commutative, right? But in addition to that, it has a property called multiplication, right? So like you've got two elements of the ring, and then we use like multiplication symbol, or we can just say AB. And then multiplication has to be defined as well, okay? So it looks like my pencil's run out of battery, but basically I'll leave it to charge for a while. It doesn't take too long to charge. But if we've got two elements A and B in the ring, then AB needs to be in the ring too, right? So that's what multiplication is. And in addition to being closed, the multiplication needs to be associative, which basically means, let me write this out real quick. ABC equals ABC. So it doesn't really matter which order you do a multiplication of 3 in, just like what we've seen with abelian groups, the multiplication will remain the same. Right, sweet. So, in addition to these two properties for multiplication, we need to prove two other properties, so distribution properties, which we've actually seen before in vector spaces and all of that. But basically, if you can prove that something's an abelian group, and you can prove those four additional properties, you can essentially prove that something is a ring. Okay? Sweet. So yeah, having looked at rings, we're going to talk about like a subgroup of the rings, right? When we say subgroup, we mean a subgroup of the abelian group, right? So recall that a ring is an abelian group that has an additional operation, or we can talk about a subgroup I of that ring, okay? So essentially what we want to do is come up with some way to make R, the quotient group of R by I, a ring. So what do I mean by that? So we've got I, a subgroup of R. I, a subgroup of R. And we need to be able to take two elements of this quotient group. So S plus I, R plus I. And we need to be able to multiply them together, because then we've formed a ring, right? The whole idea is that we've taken R, we've taken S, and now we can somehow multiply them together to form RS plus I. But in order to do that, then yeah, we've got this over here. The cosets of the subgroup will be in the form R plus I. And so multiplication only makes sense when we can take two of these groups and then formulate AB plus I. And in order for that to be true, if you expand this general expression, A plus I, B plus I, you get AB plus AI prime plus IB plus II prime. And basically, we've got AB plus all of these elements, which means that these elements over here, so AI plus IB plus IB, all need to be elements of I, right? So essentially, this is the concept of an ideal. An ideal is a subgroup of the abelian group corresponding to a ring, such that I'll write out the definition. It's a subgroup. And also, if you take any element from the ring and any element from the ideal, if you multiply them together, regardless of the order, if you multiply them together, then regardless of the order, you should get an element of the ideal. So like a classic example of an ideal is like 3z. So 3z, yeah. So z is a ring, because you can multiply elements in, you can multiply integers together, you can add them together, and you can prove that they satisfy all of those properties. So z is a ring, but if you take something like 3z, then it's also an ideal, right? Because if you take an element of this, which is 3k, so any multiple of 3, and you multiply it by an integer, then it's also in the original ideal. It's also a multiple of 3, right? And if you do it the other way, so a times 3k, because it's commutative, you'll get the same thing, right? So basically what this means is that if you want to prove something is an ideal, you just prove these two properties, but also you prove it's a subgroup, okay? And an ideal is kind of like a normal subgroup for like a normal group, right? We've got I is denoted with that same symbol. I is an ideal of R, okay? So one common mistake, so 1 doesn't need to be an R, right? So if you think about like 3z, um, 3z being in Z, it might not be a subring, right? So 1 doesn't need to be an R. Note that a subring is something where you have the multiplicative identity. So in this case, 3z is actually not a subring of Z, right? Because it doesn't have a multiplicative identity, right? It's actually going to be shown that if you have 1 in the ideal, if you've got 1 in the ideal, then you can keep on adding 1 to itself. And you can basically show that using 1, you can generate all the elements of R, okay? So it's not always a subring. All right, let's do an example that's probably more our speed right now, because we're trying to prepare for exams. Okay, so one example from 2019, we've got 2 ideals of a ring, and we want to show that the sum of the ideals, which is the set of all numbers that you can construct from summing up individual elements of each of the ideals, is also an ideal, okay? So let's have a crack at that. Basically, you need to show that it's an abelian group. And you also need to show that property, whereas like Rx and XR, for X in the ideal and R in the ring, needs to be in the ideal, okay? So let's go to our notebook. All right, so I plus j equals I plus j, for I in I, j equals j. You need to show this is an ideal, okay? Sweet. Okay, so rather simply, to show it's an abelian subgroup, we've got, let's just go to the next page. Yeah. So it's a well-known property that if you have the sum of 2 subgroups, it's also a subgroup of R, and it also forms an abelian group, okay? That part is pretty simple, but let's do the ideal thing. So we've got I plus j. We need to show that for I, an element, let's just make it less complicated, we'll do like k, an element of I plus j. And for for R, an element of R, kr and rk are both elements of I plus j. Okay, so let's try doing that. So k being an element of I plus j means that we can write k equals I plus j for I equals I and j equals j. And then let's do this multiplication thing. Kr then equals I plus j times r, which equals ir plus jr. And if you think about it, ir plus jr, because I and j are ideals, that means that this thing has to satisfy the ideal property, which means that I being an element of I, R being an element of R, must also give an element of I, right? So IR is an element of I. And then similarly, you can use the same property to prove that JR is an element of J, because we've got the ideal property again, right? So J is an element of J, and then R is an element of R, okay? So that means that we do actually have I plus J, for I element of I, and J an element of J. So it can be proven that KR is an element of I plus J. And so the reverse is also true. We won't go into it. But yeah, that's how we can prove it. Okay. So we've done the same thing over here. I'll let you read through it in your own time, but you just do the same argument. But the important thing is you start from the essential property. Okay, so let's look at K equals XY, an ideal in R. So to really do this question, we need to understand different types of ideals. So I kind of alluded to this before, But like, there's this property which we'll go through later called an ideal generated by an element. So we often write it like this or like this. And what it is it's the smallest ideal containing that element. So for example, let's take Z, the ring Z, and let's think about the ideal generated by 3. If 3 is going to be in the ring, then we need to be able to take 3, multiply it by any number, any integer, and that needs to be in the ideal. Okay? Because that's what we're actually told in the definition of an ideal, right? If you take a number in that ideal, multiply it by anything in the ring, that needs to be an element of the ideal as well. So literally any multiple of 3 needs to be in the ideal. And because it's a commutative ring, the reverse also holds, but it doesn't change anything. So 3 times k needs to be in the ideal. But essentially, once you've done that, you can show that the ideal needs to contain all multiples of 3, which is like, and that turns out to be the ideal. So the smallest ideal is actually 3z. So the ideal generated by 3 is 3z. Because it's like, once you chuck 3 into the equation, you need to be able to generate every single other ring, every single other element in the ideal from that number. Okay? So that's the idea of an ideal generated by 2 numbers. Okay? Another thing you can do is have an ideal generated by 2 numbers. So for example, one example of a ring is zx. And you'll see this notation a lot, but hopefully you've seen it in lectures. Z is the set of integers, of course, and then this x thing means the set of all polynomials in x generated with coefficients in z, right? So all integer polynomials. And so one example of an ideal is, for example, 3. And this is basically the set of all polynomials divisible by 3, right? Because you can take 3, you multiply it by any polynomial, it needs to be in the ring. So, sorry, it needs to be in the ideal, right? So for example, 3, 3x, 9x squared plus 6x, they are all going to be elements of the ideal, right? This is just the set of all integer polynomials. Divisible by 3. Okay. Yeah, that's another example of an ideal. All right. So let's go back to this. And you can also have an ideal generated by 2 elements, right? So like 3 and x is the ideal generated by 3 and x. So you can have like Alright, sorry about the delay. But yeah, back to this. So, yeah, we need to show that, it's going back to the original question, k equals xy, for x equals, x is an element of I, y is an element of j, is not an ideal, in general. Okay. Okay, so let's give that a crack. Let's just take, for example, 3x, which is, as I said before, this set over here, 3, 6, 9. And what you could potentially do is multiply it by another ideal 2x, right, which is going to be 2, 4, 6, and then x plus 2, x plus 4, and so on. Okay. So these are 2 ideals, and you want to show that, like, if you take the product of these 2 ideals, so ij, I in 3x, j in 2x, you need to show that this is not an ideal in general, okay? So, what you could do perhaps is, you know that ij what you could potentially do is think about like how you can find the elements of ij, okay? Actually, we might do another set, maybe like 2x, And this will be like 2x, 4x, 6x, 8x, and so on. But you want to keep on experimenting with ideals and just basically show that if you multiply these two together, then you won't get an ideal, okay? So we know that like this thing needs to have, for example, 6x, right? Because you have to be able to multiply stuff from each set together. 6x needs to be in it. 6 times 12x, like 12x needs to be in it, and so on and so forth. If you think about it, like if it's an ideal, it needs to be closed under the group under addition, right? Which means that if you take, like, for example, 3x from this set, and then minus 2x, or like plus 2x, it needs to be an element of the ideal as well, okay? So because 3x is an element of, sorry, one second. Let's just do the question we have over here. So like if you do 2x over here, got like 2, 4, 6, 8, and then so on. You've got all of these. Then if you think about it, you need to be able to multiply stuff from each set together, and that's going to form your group, right? So you've got like 6 is one element, and you've got like 12 is another element, and you've got 18 is another element, and so on and so forth. And you've got x plus 3 needs to be an element, x plus 2 needs to be an element, and so on and so forth. 2x plus 3, 3x plus 2 needs to be an element, and so on and so forth. But basically, you have to be able to multiply elements from each of these set together, and that will give you your ideal, okay? And so if this is to be an ideal, then what that means is that it needs to be closed under addition. So if you, for example, take this over here, take these two sets, so 2x plus 3, and subtract them from each other, then you'll get, in this example, you'll get x, right? So if this is going to be an ideal, let's just write this out formally. If k is to be an ideal, it needs to be an abelian group. Which means that you have to have 2x plus 3 minus 3x plus 2 needs to be in k. And any combination of these things needs to be in k, right? Which means you've got to have, in this case, it'll be minus x will need to be in k. But if you look at the elements we have in this set, it's not possible that we can have x in k, because to get x, you need to multiply one element from one set and one element in the other, which means one of them needs to be of degree 1, and the other one needs to be of a constant. Okay? But the issue is neither x, like 1, the constant will need to be 1 or minus 1, right? Because the only divisors of minus x that are constants are 1 and minus 1, which basically means that it's not possible for this to be constructed from the ideal. Okay? So even though if it is an abelian group, then we somehow get minus x being in the ideal, but that is not possible, right? So in this case, the product of these two ideals is not an ideal. So for these kinds of questions, you just want to test out different ideals, test out different elements, and see how assuming it's an ideal leads to a contradiction. In this case, we took like two similar elements from the group, we subtracted them, and we found that we've got minus x in the ideal, but that yielded a contradiction. So x is not in k, and hence, in general, k is not an ideal. Cool. So those kinds of questions, like, they take a bit of thought. It's hard to like come up with them off the cuff, but you want to think of possible examples. Okay, so this is another example. I won't go through it, but yeah, sweet. Alright, another similar example. Let's talk about rings and ideals. So R is a commutative ring, which means that multiplication as well as addition is commutative. Right, so xy equals yx. And in this case, we want to let I be the set of all elements such that x to the power of n equals 0. Okay, so we need to prove it's an ideal. Okay, and remember, to prove something's an ideal, there are two parts. Number one, you have to show it's an abelian group. And number two, you need to show that it's actually also it satisfies the property where Rx and Xr are in the ideal if X is in the I and R is in R. Okay, so abelian group first, we need to show that if X and Y are in the ideal, you can use the subgroup lemma so you don't have to prove like everything all at once. And the subgroup lemma has three properties. We need the 0 to be in it, we need the inverse to be in it, and we need addition. Okay. Right, basically closure under all of these. So O has to be in the group. The inverse has to be in the group, and addition means x plus y has to be in the group. Okay. So let's first consider 0. So 0 to the power of n, is that equal to 0? Yes, it is. Right, so 0 to the power of n is equal to 0. So 0, or the additive identity, is in the ring. Sorry, not the ring, the group. Oh, is in the set, I should say. Sorry, we can use I instead. Okay, that's the first part. Inverse as well. So let's suppose that x is in I. Then that means that x to the power of n is equal to 0. Then we'll consider minus x to the power of n. That's just going to be minus 1 to the power of n times x to the power of n, because we have a commutative group. Right, and that's just going to be equal to 0. Okay, so that second part is proven. What about addition? Right, so addition, we've got x plus y. So we need to be able to say, suppose x plus y are in I. That means that x to the power of x to the power of n is equal to 0 for some m, and also y to the power of n is equal to 0 for some n. And make sure you understand that in this case, they don't have to be the same, because all we need to know is that x to the power of n is equal to 0 for some integer. Like, they can be different integers with different elements, but we've got x to the power of m and y to the power of n. And now let's think about x plus y to the power of n. Because this is a binomial expansion, like, or it doesn't have to be m, but x to plus y to a power is going to be a sum of terms of the form x to the I, and then y to that number minus I. Okay. So the question is, what power do we need to put this to in order for all the terms to vanish? We know that if this power is greater than or equal to m, the power of x is greater than or equal to m, it vanishes. And if the power of y is greater than or equal to m, it vanishes. So what we can do is maybe we can set a number such that all of these terms need to have at least one of those holding. So either x is greater than or equal to m, or y is greater than or equal to n. And the way to do that is, you guessed it, to do m plus n. Because then we know that at least one of these powers, at least one of these properties will hold. Either this one will be greater than or equal to m, or this one will be greater than or equal to n. Because if it's not true, right, let's just write this out. All terms must vanish since the power of x, which is I, and the power of y, which is j, both of them cannot both be less than m and less than n. Because if it's less than So it must either satisfy I is greater than or equal to m, or m plus n minus I is greater than n. Right? Because if it's not true, if this is less than m, this is less than n, then the powers won't actually add up to m plus n. Okay? So yeah, that means that x plus y is also in the group. And so we have an abelian group. Cool. As for the next part, let's think about this. So we need to show it's an ideal. So recall that that means that if we've got x in the group, so x in the group I, and R in the ring, then XR and RX must both be in the ring. Okay, so let's consider XR. So XR equals, I don't know what XR is, but we know that x to the power of n needs to be equal to 0 for some n. Okay, so let's think about this. That means that if we take XR, and when we put, because it's an abelian group, you can just do it like normal multiplication. So yeah, that means that if you put this to the power of n, you can rearrange it, you'll get x to the n, r to the n, and that will be equal to 0. Okay. The same is true of Rx. And that means that it's an ideal. Okay. Sweet. So that's how we prove that. Just remember the two parts. So show it's an abelian group, and also show that it's an ideal. It follows the properties of an ideal. Cool. There are some basic properties of ideals that we should also know. So if you've got ideals of a ring, then the intersection of those ideals is also an ideal. If you've got a field, there are only two ideals, which are 0 and R. And if you think about it, it's because of what we said with like generation. Like in a field, you can have inverses, you can also have, basically the main thing with fields is you have inverses. But if you think about it, right, if you have any element, the ideal generated by any non-zero element in a field, then you also need to have a inverse. Okay? Sorry. Then you need to be able to, every multiple of A needs to also be in the ideal, because that's the idea of an ideal, right? If x is in the ideal, then Rx is also in the ideal, right? So every multiple of A needs to be in the ideal. But literally everything in a field is also going to be a multiple of A, because you can always just do division. So if you want to get to an element of B, you just do multiply by B, A inverse, right? So literally everything in a field is a multiple of every element. So basically, as soon as you chuck in any non-zero element, you need to get the entire ring. Okay? Yeah, so that's one way of thinking about that. Lastly, this idea of generation. So the ideal generator we talked about before is the set of all ideals that contain S, or it should be the intersection of all ideals that contain S, right? Basically the smallest ideal containing the elements of S. Okay, sweet. All right, so that's that part done. Okay. Yeah, so more information on the generation of ideals. So if I is finitely generated, which means the set S over here is actually finite, so you can write it out as alpha 1 down to alpha n, then you can express it using what's called the basis elements, right? So you can say it's generated by these elements alpha 1, alpha 2, all the way down to alpha n, right? Alpha 1, alpha 2, down to alpha n, okay? And so I is a printable ideal if it can be generated by one element, right? So I is equal to the ideal generated by alpha, okay? And this becomes useful later when we start talking about domains. All right, sweet. So this question is talking about an ideal in Zx, and as we talked about before, this is the set of all integer polynomials. We need to show it's not printable, okay? And so you might look at this and say it's generated by two elements. Of course, it's not printable. But sometimes, for example, if I say like the ideal generated by 3, 6 of Z, that is actually the same thing as the ideal generated by 3, right? Because 6 is unnecessary. It's like if you have like a vector space made out of like three elements, right? And then like two of them are like linearly dependent, then one of them is useless. It's the same kind of idea. The 6 over here is useless. So it's not true that just because we've got two elements here, it's like it's not principal. You have to show that it's not possible to rewrite this. It's not possible to rewrite alpha is 3x cubed minus x squared plus 2x minus 1. Okay. Sweet. So yeah, we need to basically, sorry, that should be spelled principal. But yeah, suppose that the ideal is principal, which means that there exists an alpha such that it's equal to that. And that means that alpha needs to generate both 3 and also x cubed minus x squared plus 2x minus 1. Which means that alpha needs to divide 3 and alpha needs to divide x cubed minus x squared plus 2x minus 1. Okay. Now there aren't many options if alpha divides 3, because in this set of like polynomials, like integer polynomials, you can only have like 1, 3, or minus 1, minus 3. Okay. And so we're going to go through these possibilities and show that they all don't work. Okay. If alpha equals 1, then it's the ideal generated by 1, which means it's the set of all multiples of 1, which is just the original ring. Okay, so yeah, it's the original ring, which means like we've got a bit of an issue, because obviously this is not the entire ring, because 1, for example, cannot be generated from 3 and x cubed. X minus 1. Right, so it can't be 1, also can't be minus 1 for the same reason. What about 3? Okay, that's the other option. If it's equal to 3, then the other condition doesn't really hold, because 3 doesn't generate x cubed minus x squared plus 2x minus 1, which means that we won't have a solution there either. Okay, so the formal way of writing it is this: a has to divide both of these, but also a can't be equal to 1, and then a can't be equal to 3. Okay. Sweet. Alright, next definition. So we've got an ideal of R. So for I an ideal of R, we say it's maximal. We say the ideal is maximal if we've got this over here. And then if we've got an ideal between them, so I is a subgroup, I is a subset of J is a subgroup of I, then if J is an ideal, then either J is equal to I or J is equal to R. You can't have like any non-equal sets like sandwiched between them where J is also an ideal. That's what maximal means. Okay? That is, if J is an ideal of R and we've got I a subset of J, a subset of R, then either J is equal to the left one or J is equal to the right one. Okay? Sweet. So a theorem that we can use, which is often used to prove that something is maximal, because you can imagine this definition is quite hard. I is maximal if and only if the quotient ring R divided by I is a field. Okay? So if you can show that R on I is a field, then you've shown that I is a maximal ideal. Okay? Sweet. Another type of ideal is prime ideals. So let's think about that. So basically, I is a prime ideal if RS being in the ideal. So RS being in this ideal implies that one of these two needs to be in the ideal. Okay. So either R is S, R is in the ideal, or S is in the ideal. Right. That's what prime ideal means. And a common example is prime numbers. Right. So if you think about the ideal 5Z. If you have a number x in 5z, then x is a multiple of 5, which means that if you've got rs being in 5z, that actually means that r times s is a multiple of 5, and because 5 is a prime number, one of these two needs to be a multiple of 5. You can't somehow have like root 5 here that combine to make 5, because they're not integers. There are no other divisors. One of these two needs to be divisible by 5. right? That's the same kind of idea as an ideal. If you've got RS, an element of an ideal, then at least one of them needs to be in the ideal. Okay? One thing you can do is you can say a non-zero element of a ring R is prime. Okay, I'll explain what prime means in a second. If and only if the ideal generated by P is prime. And so a prime number in the context of group theory or ring theory is very similar to what it is in real life, or like in integers, right? So like, basically P dividing RS implies that P is divisible by, or that P divides R, or P divides S. That's what it means for a number P to be prime. Okay. But yeah, there are these two definitions of prime things that are very interrelated, and they're worth remembering. Okay. It can be proven that a maximal ideal is a prime ideal, which means that maximal is a subset of prime ideals. But the converse is not true, which means that there are some prime ideals that are not maximal. Okay. Sweet, let's give this a crack. Let's do this example from 2022. Okay, it's quite a long example, but let's get through it. So prove that an integer prime P is a prime element in R. Right, so prime element in R we remembered before. If and only if x squared plus 3 is irreducible in Fpx. Okay. And there are a lot of definitions here, but let's remember what prime means. So prime means that if P divides Rs, then that means that P divides R or P divides S. Okay, and irreducible is something we'll learn later, but basically irreducible means that you cannot factorize it. Oh, we'll talk about it. Well, maybe I'll just scroll down for a bit. We'll talk about this before we actually go through that. Yeah. So basically, sorry, should be over here. So a non-zero and non-unit element R is irreducible if every factor of R is either a unit or an associate of R. Actually, what we might do is we might get back to this later, because there's a lot of theory that goes into it, so we'll come back to this question later. Okay. But yeah, it's quite a long question, so we'll go through that afterwards. Okay, let's move on to the next concept. So that's the Chinese remainder theorem for rings. Okay, so the Chinese remainder theorem is kind of like, we've got information about x, okay? Information about x. So x is equivalent to one number mod n1, it's equivalent to another number mod n2, and equivalent to a kth number, ak, mod nk. And it turns out that using this information, you can convert to and back to what the number is modulo n1, n2 down to nk, right? So that's basically what this statement is saying. It's saying that if you have information about x modulo a bunch of numbers, you can convert it to the number modulo the product of those numbers, as long as each of the pairs of integers is co-prime, okay? So it's the same thing as what it said over here. Like for any a1 down to ak, there exists a unique solution to the simultaneous equations, okay? Basically, that is equivalent to the overall statement, and I'll explain it in a second, for rings, okay? So these two sets are isomorphic. If you've got I1, I2, and they're all ideals of this ring, okay? And what you do is each of them sums up to create R, right? So I plus IR sums up to create the entire ring for each pair, okay? And what we do is we say, we take the intersection of the ideals, and it turns out that the quotient ring over the intersection is equivalent to the product of the quotient rings over the individual ideals, right? So in other words, all of this information, remember an ideal is like, for example, 3z. R plus 3z plus r plus 5z all the way down to, let's say, 13z. All of this information tells you what it is mod 3, for example. It tells you where it is in reference to this first ideal. Then it tells you where it is in reference to this ideal. Then it goes down and down and down. And then this last piece of information tells you where it is in reference to the ideal 13z, which is just what it is modulo 13. Okay? And then all of that information is equivalent, so hence the isomorphism, to the information mod all of these numbers multiplied together. So 3 times 5 down 13z, because that is the intersection of these, right? So in other words, let's just go back to what this statement is saying. R divided by the intersection, or the quotient ring of R over the intersection, is equivalent to the direct product of all of the individual ideals. Okay? That's what this statement is saying. But to do this, we need to have this property over here, which is that each of the pairs of ideals adds up to R, the entire ring. Okay, let's get through that. All right, so let's look at this. So we've got two maximal ideals, M1 and M2, in the commutative ring R. Okay, and we've got I at the intersection of M1 and M2. All right, let's think about what that means. If M1 and M2 are elements of R, and we want to show that R, the quotient ring of R over I, so the intersection of these two, is isomorphic to a direct sum of two fields. So thinking about this requires us to use the Chinese remainder theorem, because we've got R quotiented over an intersection, and then that's going to be, provided that we satisfy the requirements of the Chinese remainder theorem, it's going to be isomorphic to R divided by M1 plus R divided by M2. Okay. All right. But think about that. What it actually means is that we actually need to show the property, which is that M1 plus M2 is actually equal to R. Okay, so let's go to the other page. And you can hopefully see the flow of logic. So it's always good for proof questions just to map up like what we need to prove. We need to apply the Chinese remainder theorem. And then if we can show that this statement is true, we can apply the Chinese remainder theorem and show that this is true. And then think about this. Each of these is R quotiented over a maximal ideal, which is isomorphic to a field because of what we had in the theorem before, right? So that's a three-step process. Let's write this out formally. Okay, so we need to show that M1 plus M2 is equal to R, because that's required to prove the Chinese remainder theorem. So think about M1, M2, and R. We know that this is going to be a subset equation. So M1 is a subset of M1 plus M2, subset of R. And what that means is that because M1 is a maximal ideal, and we know that M1 plus M2 is also an ideal, because this is maximal, it's kind of like the squeezing theorem, right? This is either equal to M1 or it's equal to R. But M1 is not equal to M1 plus R2, because we're given in this information that M1 is not equal to M2, right? Which means there are elements over here that we don't get over here, right? Because there are elements that we've got in M2, they're both maximal, so these can't be equal. So that means that M1 plus M2 needs to be equal to R, since M1 is maximal. Okay, cool. That's the first thing we've proven. So now we've proven that this requirement of the Chinese remainder theorem. So let's just take that out. So by the Chinese remainder theorem, we've got this divided by M needs to be isomorphic to that sum. But we know that I on M1 is isomorphic to a field, and so is this one, since both ideals are maximal. And so combining that all together, we know that I quotiented over M is isomorphic to the direct sum of two fields. Right? And hopefully that will make sense. Sweet. So we can write that all out, but that's just the same thing that we've just shown before. Yeah, and that's the Chinese remainder theorem. All right, let's have a quick look at integral domains. So a ring, a commutative ring, we can only do this for commutative rings, which means multiplication is commutative, so Rx equals XR. It's going to be called an integral domain if the product being equal to 0 implies, as it does in like normal integers or normal like real number algebra, that R equals 0 or S equals 0. And this is also sometimes referred to as the no zero divisor property. So no number goes into 0. So for example, in the ring like 5z, also in the ring 6z, in the ring z on 6, 2 times 3 equals 0, right? And that actually means that it's not an integral domain, because we have a 0 divisor. Right, sweet. Alright, so why is this useful? In an integral domain, the cancellation law applies, right? Because if we know that uv is equal to uw, you can subtract from both sides. You've got uv minus uw, and you've got u v minus w, which implies that v is equal to w, because we're assuming that u is not equal to 0. Okay, so basically you can cancel out numbers that are not equal to 0, because we've got a domain. Okay. And so what's interesting is an ideal is prime if and only if, it should say if and only if, the quotient ring R quotiented over I is an integral domain. And you can see why like a prime ideal is a subset of maximal ideals, right? Sorry, not a subset, it's a superset of maximal ideals, because if you have a prime ideal I, then R on I is, sorry, let me write this out. R on I is a domain, but if you have a maximal I, then R on I is actually equal to a field, which is a stronger property, right? So because field is stronger than domain, maximal is stronger than prime, right? So hopefully that helps you remember these two properties. But yeah, if you do R quotiented over I for a prime ideal, then the quotient ring forms a domain. Okay. Let's have a look at this question. So z plus z in integral domain. Well, let's think about what z plus z is. It's the set of all productive integers. Set of all direct productive integers. So like 1, 2, combinations of two integers. And when you multiply them together, you do it coordinate-wise, right? So 1, 2 times 1, 2 equals 2, 4. Sorry, 1, 4. Well, if you think about it, like, the question is, does this have any 0 divisors? So is it possible to get two numbers that are both not equal to 0, multiplying to give you 0? Well, if you think about it, if we've got a 0 here, and a 1 here, and a 1 here and a 0 here, then that's equal to 0, 0. And that means we have 0 divisors, which is not allowed. Right? Sweet. So it's not an integral domain. Sweet. Alright, the reason why we like domains is because we can take domains and extend them to what's called fields. So we'll talk more about fields in depth later, but a field is just a domain where we have certain like properties, such as inverses, right? And if you take an integral domain and you consider the fraction field, a fraction field is basically a set of all numbers, and a nice way of writing it is just, let me just write this out. Basically, if you've got A and B in a domain, then S, the fraction field, in a way you can think of it as the set of A on B. But the thing is, we can't really define division we can't really define division in a domain. So what you do is you get around this, you say it's a set of all numbers A, B, where basically you have two fractions being equal if A on B equals C on D, or like, because we can't divide, we say AD equals CB, right? That's why we have this fraction over here, right? So basically this is a way of basically jumping around the fact of fractions, but essentially a fraction field is just a set of all like ratios of two numbers in the domain, right? And that's going to be an integral domain, okay? All right, and we denote the fraction field of D as KD. So for example, if you take integers, an integer is an integral domain, but it's not a field. If you extend that to a field, you get a set of rationals, right? And the rational numbers are a field, okay? So some properties of fractional fields. If f is a field, then basically writing the fractions of a field is just the same as the field itself, because a field already has all fractions. You've already defined division in a field, so in a field you can actually do A on B already, and that's already an element of the field. So kf is just equal to f. If S is a subring of R, then Ks is a subring of Kr. Taking the fractional field doesn't change that property. And if R is a subfield of R, then Kr is also a subfield of Kf, which is equal to f. Okay, sweet. Alright, so now we look at the concept of factorization. And factorization is useful for a ring or a field because we have these things called unique factorization domains. Factorization means the same thing as it does in integers. It's like writing a number. It's like 5 equals 5 times 1, or 6 equals 3 times 2, as a product of other factors, right? But to extend this concept to something beyond positive integers, we need a few like definitions first, right? So in Z, it's pretty simple to say you've got a unique product of primes up to reordering. But for example, if you've got something like Z square root of minus 5, factoring 6 into 3 times 2, or you can also do this. And these are all valid numbers, and you can show that they're all prime. Right, so 3 and 2, and also 1 plus square root of minus 5, and 1 minus square root of minus 5, they're all prime. So you don't actually have unique factorization. So to actually define unique factorization, you need a few properties of a domain. But yeah, not all domains have unique factorization, as we just showed. But before we talk about that, we have to talk about some definitions of factorization theory. Okay, so R is a factor of S. It's pretty simple. If there exists some number in the ring or in the domain such that S equals RT. So you can take R, multiply by something, and you'll get S. Okay. That's what factor means. Two numbers are associate if there exists a unit. So a unit is an invertible element. A unit is an invertible element. So R and S are associates if R equals SU, right? So you can take an invertible element, multiply it by one number, and get the other number. So for example, in Z, 5 and minus 5 are associates because you can multiply it by minus 5, and you'll get the same thing, all right? So, like, the whole point of associates is that these numbers are basically the same. If you can multiply a unit in there and get a different answer, that's basically the same thing because units are invertible, okay? And if you have an element that's not a unit, it's also not 0. It's irreducible if you can only factor it into other units and associates, which means you cannot break down something like, so for example, 6 you can break down as 2 times 3. But 5, you can do 5 times 1. You can also do minus 5 times minus 1. But all of these elements are either just the same thing like 5, or they're units themselves, so 1 and minus 1. Okay? So irreducible means there are no non-trivial factorizations. And last of all, as we said before, an element is prime if P dividing Rs implies that P divides R, or P divides S. Okay. Sweet. So looking at unique factorization domains, gonna take a drink of water. There are some properties. So you can imagine we talked about an ideal generated by S as being the set of all multiples of S. Because you take S, you multiply it by an element of the ring, needs to be in the ideal as well, right? So R divides S if and only if one of the ideals is a subset of the other one, right? The bigger one, the one that divides it, or the one that is a multiple of the other one, is going to be a subset of it, right? So for example, like 2 and 4, this one is just a subset of 2 because it's just more strict than 2, because 4 is just a multiple of 2, right? And two numbers are associates if and only if their ideals generated are the same. So for example, 5 is the same thing as minus 5. A non-zero element and non-unit element P is irreducible if and only if the only principal ideals that contain P and 1. You can't go in between, right? That's what irreducible means. You can't go in between to like root P. And so finally, a non-zero and non-unit element P is prime if and only if this is a prime ideal. So that's that one-to-one relationship between primeness and prime ideals. Yeah. And so it can be shown in the commutative domain that every prime element is irreducible. Right? So if you've got a prime element, it must therefore be irreducible. But it's not always true that an irreducible element is prime. Okay. Sweet. So now we're building up to this final thing called UFDs, which are unique factorization domains. Okay. So a unique factorization domain is a domain where these properties hold. So for any non-zero and non-unit element R, you can write R as a product of irreducible elements, and this method of writing it as a product of irreducible elements is unique, right? Which means that the number of elements is always the same. So if you've got two factorizations, the number is the same. So P1 down to Pm, Qm1 down to Qn, then that means that M is equal to N. And also we can reindex P1 and Q1 so that we always have associates. All of the corresponding elements are associates, right? So P1 is an associate of Q1, P2 is an associate of Q2, and so on and so forth. Where associates are basically the same thing. Okay. So an example is over Z. So Z is a really useful example to get your head around stuff. So 10 equals 5 times 2, but also 10 equals minus 5 times minus 2. So it's not unique, but it's unique up to associates, because 5 is an associate of 5, and 2 is an associate of minus 2. Okay? Alright, so let's have a crack at this. So how would we approach a question like this? Show that 21 does not factor uniquely as a product of irreducibles in Z root minus 5. Okay? So let's think about it. We want to break 21 down into its factors. So one obvious way is just to do it the normal integer way. So 21 equals 7 times 3. And are these two numbers going to be irreducible? We can think about that later, but let's just try to think of another method of breaking this down into a product of two elements of Z inverse minus 5, of Z square root minus 5. So if you do something like A plus B square root minus 5 times C plus D square root minus 5, then, well, for it to be equal to a real number, they need to be conjugates of each other, okay? So basically we'll have something like A plus B root minus 5, A minus B root minus 5, okay? How can we get numbers A and B such that this product is equal to 21? Well, for example, you're always going to get, the answer will be A squared plus 5B squared if you do this multiplication. So thinking about that, like, what could A and B possibly be? If you have B equals 1, for example, you've got 5, and the other part needs to be 16. That works, right? Because we've got 4, and then B will be equal to 1. So 4 plus root minus 5, 4 minus root minus 5. Okay, so that's a way of breaking it down into two products but we now need to show that it's a product of irreducibles, okay? So we now need to show that these are two distinct definitions, right? Where each of these elements is irreducible, and therefore that we've shown the statement, okay? So how will we generally do that? Generally what we do is we say we take each of these elements, so let's take 7 for example, and try to write 7 as a product of, let's go to a different page, okay? So we need to show that 7 is irreducible, okay? Which means that, remembering what we said before, if we write 7 equals a plus b square root minus 5 times c plus d square root minus 5, then one of these elements needs to be either a unit or an associate. Oh, sorry, no, one of these units, like a plus b square root minus 5, needs to be either an associate of 7 or a unit, okay? Sweet. Let's give this a try. What we can generally do is expand this out, so we'll get ac minus 5bd plus AD plus BC, square root minus 5. That gets quite complicated actually. So what we tend to do in these questions is we tend to, another method if that doesn't work is to use a modulus, because I was already seeing that was getting a bit complicated. So we can take the modulus of both sides. So 7 equals square root of a plus 5b squared, square root of c plus 5d squared. And then we'll square both sides just to make it more simple. 49 equals a squared plus 5b squared times c squared plus 5d squared. This should be squared. Okay, so looking at this now, we need to basically show that if this holds, it's going to be some kind of contradiction. Okay, so these are all integers, which means they must divide 49. So a squared plus 5b squared and c squared plus 5d squared, they need to both be elements or divisors of 49, which means they have to be 1, 7, or 49. Okay? So let's think about each of the options. If we've got a squared plus 5b squared equals 1, then that means that b equals 0 and a equals 1, right? Because like once b gets bigger than 0, it's like 1 or minus 1, it's already bigger than 1, right? So that's the only solution to this, or a could be plus or minus 1. But if that's the case, then a plus b square root minus 5 is equal to minus plus or minus 1, which is a unit. Okay? And that's actually what we want, right? Because we want to show that the only divisors are units and associates. That's good. Okay? What if it's equal to 7? Think about that. So b can't be equal to 0. So b can't be equal to 0. Because then a squared equals 7. So a equals root 7, which is not an integer. Okay, that's good. What if b equals 1 or plus or minus 1? We're going up in the grades. So plus or minus 1. So that's also not possible because then a is equal to plus or minus 2. Right? Sorry, a squared equals 2. Sorry, let me write this out. So b equals plus or minus 1 means that a squared equals 2, which means that a equals plus or minus root 2, which is not allowed either. Okay? And then as we go up in b's, b being equal to plus or minus 2, also not possible. Because then we got like 20 over here, then a squared has to be negative. So, and so on. There is no integer solution. Okay. So, also good, right? We've shown it's either a unit, no solution, or the last one is if this thing is equal to 49. But if that's true, then think about it. C squared plus 5d squared equals 1, which means it's also a unit. Right? And what that means, basically, is that no matter what, there'll be a unit in there, right? So this is definitely irreducible. And you can do the same thing with all of the other elements. So you can do the same thing with 3, same thing with 4 plus root 5, and same thing with 4 minus square root minus 5. Okay? And if you do all of those, then you'll show that it's not factoring uniquely as a product of irreducibles. Okay? Sweet. So, yeah, this is a formal way of writing it out. But yeah, you can look at this afterwards in the slides, and this is basically how that works, right? So you want to show that all of the elements are irreducible, in which case it's not actually factoring uniquely, which means I can also write this out. This is not a UFD. It's actually a well-known result that z root minus 5 is not a UFD, whereas something like z root minus 3 is, right? It's just a matter of different factors. Okay. Sweet. All right, let's look at a different type of domain. We might take a very quick break so I can get a glass of water. I'll be back in about 2 minutes. All right, sweet. Let's get back onto it. So this is a different type of domain. We've already talked about UFDs. UFDs are really helpful because we have that unique factorization property. But now we've got a different type of domain called the principal ideal domain. Okay, and basically, like, let's just revise our theory. So if R divides S, then the ideal generated by R is a superset of the ideal generated by S. Okay, and if R and S are associates, then their ideals are equal, right? And irreducible elements satisfy this property. And last of all, an element is prime if and only if this ideal is prime. Okay, so those are just some useful properties we've talked about before. But a principal ideal domain is a domain where every single ideal is principal. Okay, every single ideal is principal, right? And so in this principal ideal domain, it can be shown that every irreducible element is prime, right? And we also know that it's true that every non-zero element and every non-unit element can be factored into a product of irreducible elements. And so you can actually do some working out from here to show that in a PID, you also have the UFD property. Right, every non-zero and non-unit element can be factored into a product of irreducible elements, and then that also means that that's unique, right? That method of factoring is unique. Okay, so it turns out that PIDs are UFDs, so PIDs are a subset of UFDs, and we'll talk about this last one over here later. Okay. Cool. So let's do an example. Let's show that Z, the set of integer polynomials, is not a PID. Yeah, okay, interesting. So what you want to do is, we've talked about this before, you want to generate an ideal with like maybe 2 elements and show that it's not possible for it to be generated by 1 element. So for example, 2 and x is just the set of all ideals generated by 2, to 2, 4, 6, 8, so on. Then you've also got x, right, and x plus 2, x plus 4, and then you've also got 2x, 2x plus 2. So it's got this weird structure where the constant term always needs to be even, but you can have literally any other term of higher degree, right? Because you can have x, you can have 2x, you can have 3x squared plus 4x minus 5x cubed or whatever. You can have any multiple of x, but the constant term always needs to be even, right? So what you want to do is say, let's suppose this is a PID. So suppose, let's just do a new page. So suppose Zx is a PID. Then every ideal is printable. Okay. And if every ideal is printable, then think about it, that ideal we just talked about needs to be printable. So what you will need to do is show that, assume that it's generated by a single element, and then show that that somehow leads to a contradiction. Okay. Right, so that means that 2x is printable. Alright, so that means that suppose that 2x equals a, okay? Which means that a divides 2 and also a divides x, right? But there are very few options for that, right? Because that means a is equal to plus or minus 2, plus or minus 1. But then a is not equal to plus or minus 2 since it divides x. And that means that a is equal to plus or minus 1. But then what does that imply, right? That implies that the ideal generated by I is equal to the entire ring. And what that implies, and that's a contradiction because in this ideal, for example, 1 is not in the ideal. 1 is not in 2x. And that means that's a contradiction. So not PID. Okay. Let's go down and we'll move on to the next concept. Alright, Euclidean domains. So this algebraic domain gives us properties of factorization even stronger than PIDs, which means that we'll see this later, ED subset of PID and it's not equal subset of U of D. Okay. Basically, you need this Euclidean function. So nu is used to denote what's called an Euclidean function, and it needs to map the domain to the natural numbers. And if it satisfies these properties, so nu of f is less than or equal to nu of fg, and then somehow you can do a factorization. I'll show you what this means, but you've got an f and you've got a g. You need to be able to divide f by g to get g cubed plus r, where r is either equal to 0 or r is less than the original number. So r is less than, has a Euclidean function less than g. Okay? And basically what that means is you can basically, there's this property where the GCD of g and f is equal to the GCD of g and r using this function, right? And you've seen this before in discrete maths, but let me highlight this. What this means is that you can basically keep on reducing this Euclidean function, keep on doing this division algorithm, right? And then you'll go from evaluating f and g to g and r, and you'll keep on going down. As you keep on doing the algorithm, the Euclidean function will keep on going down, and you'll eventually end up at 0, right? So any two elements, you can do that algorithm, and you'll end up with a GCD. But that's a more complicated topic that we won't go into too much right now, but it's useful for a lot of questions involving Euclidean domains. Okay. If this function exists, then D is called a Euclidean domain, right? So as we said before, we've got ED, subset of PIDs, subset of U of D. Okay. All right, think about Z square root of minus 5. Is that a Euclidean domain? So we'll think about that. ED, subset of PID, subset U of D. We already showed from before that it's not a U of D. And that actually implies that if it's not a UFD, it can't be any of these, right? Because UFD is weaker than these two, right? So that's really all you need to do. It's actually really hard to show by itself that a number is not Euclidean. Generally, you'll need to show it's either not a PID or it's not a UFD, sorry. You'll need to show it's either not a PID or it's not a UFD, sorry. And then you can show it's not an ED, okay? So yeah, 21 did not factor uniquely from before. So Z square root of minus 5, not a UFD, and therefore not a Euclidean domain. Okay. So we'll move on to the final stretch, which is talking about fields. So Gauss's lemma, right? This is a lemma about polynomials. So recall that if you can define a polynomial defined by a ring, Rx, which is basically just the set of polynomials with elements of those rings as their coefficients. Now, f is primitive if all of the coefficients are co-prime, which means the greatest common divisor amongst the coefficients is equal to 1. So for example, an element like 3x squared plus 5x plus 7, all of these elements are pairwise co-prime, which means, all of these elements are co-prime, right? The greatest common divisor among the coefficients is equal to 1, which means that it's primitive. So these two examples, 3x squared plus 6 is not primitive because the greatest common divisor is equal to 3. Okay. So Gauss's lemma tells us that if f and g are primitive, then the product is also primitive, right? If you take two, basically that means if you take two polynomials and they don't have a common factor between all the coefficients, then there's no way you're going to get like a 3 suddenly come out of it. Right? If these are all co-prime, we've got like x squared plus 1, x squared plus 5, 5x plus 2. There's no way you're suddenly going to get a number come out of it. You're not going to get a non-primitive product. This is not possible. Okay? That's what Gauss's lemma is saying. Okay? Alright, so on that basis, if you use Gauss's lemma, it turns out that the irreducible elements of Rx, which is a set of polynomials with coefficients in R, they're all either irreducible elements of R, or they are primitive polynomials that are also irreducible in Kx, where K is a fraction field. What does this mean, right? What does it mean for a primitive polynomial to be irreducible in Kx? It means you can't make a polynomial out of fractions you can't make a polynomial out of fractions and then somehow produce a polynomial that's not a fraction, is what it's saying. So if they're irreducible in Kx, it means you can't take fractional polynomials and get them to make the original ring polynomial, right? This is not possible, right? That's what it's saying here. So the irreducible elements of Rx are going to be primitive or irreducible elements of the ring itself, okay? And so we won't go into the technicalities of how this proves this, but we also know that as a result of this, if R is a UFD, then R of x is a UFD. So for example, we know that Z is a UFD, so Z of x is also a UFD. There is exactly one factorization of all integer polynomials up to reordering and associates and units, okay? Sweet. Alrighty, so we're going to finish off with fields and their extensions. So as we alluded to before, if you take a ring and you add certain properties, you can get to a field, right? What exactly is this? So to have a field, we require R to contain the multiplicative identity, right? R needs to contain the multiplicative identity, which is 1, right? So to make a field, you can't just have something like 3z, right? This is a valid ring, but it's not a field. So to make 3z into a field, you need to add 1, for example, right? But that's not all you need. You also need to have a commutative domain. And also, you need to have a multiplicative inverse of everything. That's the big one, right? Because before, for example, Z, you have like 1, 2, 3, 4, 5, and so on. The only unit is 1, or minus 1, right? None of the other elements are units, because none of them are invertible. Alright, so the concept of a field extension. Basically, you've got a field E, and you want to add in new elements to E. And so the question is, what sorts of elements do you include for the bigger field to remain a field, right? So for example, we've got the field of rational numbers. If I want to add in square root 2, what do I have to do to make this a field, right? And this is the concept of a field extension, okay? So E is a field, F is a field, then F is a field extension of E. And then we call F on E a field extension. Alright, now imagine you've got a bunch of elements in F, and then E, A1, with this bracket notation, so you write the brackets and you write all of the elements, is the smallest subfield that contains the elements E and also alpha 1, alpha 2 down to alpha n. So the thing I said before, Q root 2 is the smallest field containing Q and square root 2, okay? And so an extension is simple like this one if it's in the form E alpha, okay? All right, so there are different types of field extensions. The more simple ones are algebraic field extensions, okay? So for example, square root 2 is actually called an algebraic number. I'll explain why in a second. But what I can do with square root 2 is I can actually add square root 2 to the set of like rationals. So I'll do Q. This is P on Q. But what I can do is square root 2, I can do P on Q times 1 plus P on Q times square root 2. Sorry, not P on Q, but a different number, M on N. Right? And this is actually itself a field, because what I can do is I can multiply this by itself, I can divide it by itself, and so on and so forth. And the whole reason for that is if I take two rationals, a plus b square root 2, c plus b d square root 2, I will always get a function of square root 2, right? Because if I expand this out, I won't actually expand it out, but I'll only get like a coefficient of 2 and a coefficient of square root 2 and a coefficient of 1, right? And the whole point is that I can basically just add square root 2 to this field, and then it'll be a field itself, okay? So more formally, alpha is algebraic if it's the root of a non-zero polynomial p with coefficients in e, right? So for example, square root 2 is the root of x squared minus 2, right? And because of that, we know that we can write let me just write this out. Because square root 2 is the root of x squared minus 2 equals 0, we actually know that we can write actually, one second. Yeah, so by the first isomorphism theorem, we didn't go through this for rings, but there's a first isomorphism theorem that is the same as for groups, right? So if you've got a mapping, a ring isomorphism, so let me just write this out. Pen keeps on going out of battery, which is kind of not the best, but give me 1 second. Alright, so a ring isomorphism is just something mapping between two rings. But for a ring morphism, if you take R and you divide it by the quotient over the kernel, it's isomorphic to the image. Okay. Right, so that's the first isomorphism theorem. And basically what we've done is, if you've got a non-zero polynomial P, and P is irreducible, which means it's the smallest possible polynomial containing alpha, then it's true that E of alpha is isomorphic to E of x quotiented over P, right? And what that means is that, like, if you think about it, this is the kernel of the evaluation map. The evaluation map maps a function to its function value at alpha, right? And the reason it's the kernel is because if a function is going to be equal to 0 at alpha, it needs to divide, it needs to be a multiple of the minimal polynomial, right? And then the quotient, or the image of it, is going to be the function of all, is going to be basically the function of all the field that you generate from getting alpha, right? So basically the field that you get from adding alpha to E, okay? So the whole point of this is that if you have a minimal polynomial of a certain degree, then Px is that minimal polynomial, and you can use this property. Otherwise, alpha is going to be transcendental, which means you can't actually write it as a root of a polynomial with coefficients in E. So it's actually what we call an infinite field extension, but we'll talk about that later. So one useful thing you can use to find irreducible polynomials, so often you'll be required to do stuff involving polynomials using this property. So like E of alpha is equal to E of x quotiented over the ideal generated by P. Okay? And in order to show this property, you need P to be the minimal polynomial, which means you need a criterion for working out whether a polynomial is irreducible or not. Okay? So what we can do over here is, if you've got a polynomial like this, a0 down to an, x to the power of n, then if there's a prime such that p0 divides a0 up until an minus 1, but p doesn't divide an, and p squared doesn't divide a0, then f is actually irreducible over k. Okay? So this is actually sufficient to determine whether f is irreducible or not. Okay? So let's do an example over here. Let's do the minimal polynomial of alpha equals the square root of 5 plus 2 root 2 over q. Actually, let's make it a bit simpler. Let's because of time, we'll just change this to alpha equals 5 plus 2 root 2. Okay. Let's find the minimal polynomial of that over q. Okay. So we're trying to find a polynomial that has this as a root, which means we need to do stuff to this to get it down to a rational number. So very simply, a common technique is just to do a alpha minus 5 all squared equals a. Okay. And that means that a alpha squared minus 10 alpha plus 25 equals 8. Okay. Which means we've got alpha squared minus 10 alpha plus 17 equals 0. Okay. Just 1 second, sorry. Sorry. Yeah. Okay. So, if we want to show this as irreducible over, the rationals, then you can actually try to factor this. So this is going to be equal to 8 alpha minus 5 plus 2 root 2, alpha minus 5 minus 2 root 2. Okay. And you can show this just by doing the quadratic formula. And you can show that both of these factors, both of these linear factors that divide it, both linear factors, are not elements of Z element X, and therefore this polynomial is irreducible. It's irreducible over Zx. Okay. Because the only factor over here is this, and therefore it's a minimal polynomial. So a very simple first example. They're basically showing that because you can only break it down into linear factors that include irrational numbers, it must be irreducible over Zx. Okay. Sorry, in this case it's Qx. All right, sweet. All right. So now we're going to talk about the degree of an extension. So if you look at E, a subfield of F, and F an extension of E, then you can think of F as a vector space over E, right? And the reason why you can do that is because, okay, let's think about the degree of the extension. Let's just say this is an extension by, let's just say we've got F equals E alpha, where the degree of the minimal polynomial is P. Okay, if that's the case, then the dimension of F over E is actually P. And why is that? Because if the degree of the minimal polynomial is P, then that means that there is some polynomial. Let's just do this. P of x equals AP x to the power P plus AP minus 1 x to the power P minus 1, and so on and so forth, plus A0, such that this is equal to 0 for alpha, which means you've got AP alpha to the power P plus AP minus 1 alpha to the power P minus 1, and so on and so forth. So what you can do is you can actually rewrite AP as a function of these properties of alpha to the power of P minus 1, alpha to the power of P minus 2, and so on. Right? So I'll write this again. So alpha to the power of P is expressible as a linear combination of alpha to the power of P minus 1 all the way down to alpha 0. And in fact, you can extend this further. Alpha to the power of P plus 1 is expressible as a linear combination of these numbers as well. I'll just write it again. Right, so alpha to the power of P plus 1 is expressible as a linear combination of these. So in reality, all of these things, alpha to the power of P minus 1 all the way down to alpha to the power of 0 or 1, they are sufficient to express all elements involving alpha. They are sufficient for expressing all elements involving alpha. So if you have alpha to the power of like 79, you can express it as a linear combination of these. Because if you rearrange this equation, as I said, to make this the subject, you've got it as a linear combination of the other ones. So let's just write this as a result. This is a basis, right? So alpha to the power of P minus 1, alpha to the power of 1, alpha to the power of 0 is a basis for the vector space E alpha over E if P is the degree of the minimal polynomial. Okay. So, for example, before, our minimal polynomial had degree 2, like over here, from before. Minimal polynomial had degree 2. That means that you have a vector space made up of the basis 1, and then we have 5 plus 2 root 2. And that is a vector space for the field extension. Okay? So that's a very useful property to know. Whenever you have any field extension where the minimal polynomial has a finite degree, you can write all of the powers of that number up until the degree minus 1 as a basis for the vector space. Okay? Sweet. Let me just rub this out. Yeah. So the degree of the extension field is precisely the degree of the minimal polynomial. And you can actually construct a tower of extension. So let's say I want you to find out like the degree of FAB over F. Well, that's a bit more complicated because like, how do you find the minimal polynomial of A and B over F? Well, what you can do is you can write this as F, a field extension. So we know that we can break it down in step by step. So we do the field of AB over field of B, and then we multiply that by FB over F. Okay, so that's this property over here. If you've got 3 fields, and in this case we've broken it down step by step, you can write out H indexed by E is equal to H indexed by F times F indexed by E. Okay? Sweet. Let's give this one a crack. Okay. This looks really complicated. We've got a bunch of p's, but we can rewrite these all in terms of a given number. So 1 plus p root of p plus p root of p to the power of 3, all the way down to p root of p to the power of 2p plus 1. Okay, so in other words, this is all made up of the p root of p, which means that this is actually a subset of the field extension of Q by the p root of p, right? In other words, this thing is actually a subset of this. Because remember, once you add a number alpha to a field, you need to have all powers of it. Because a field is like everything that you can make from multiplying and dividing by a given number. So if we have this number in our field, right, if we have the p root of p into the field, we need to have this in our field too, right? So Q of theta is actually a subfield of this, right? And then you can construct a further tower. You've got Q is actually a subset of that, okay? So let's write that out. Since theta is a polynomial in the p root of p, we can write Q is a subfield of Q p root of p, which is a subfield of Q alpha. Okay. Sorry, no, wrong way around. Q is a subfield of Q theta, subfield of Q p root p. Okay, sweet. All right, then you can construct a field extension. You always write the tower of extensions. We're trying to find this number. Oh no, sorry, we're not trying to find this number. This is equal to this. Okay, sweet. So we're trying to find this number here. Do we know this number? Let's think about this number. So p root of p, what do we think is the minimal polynomial of that over q? Well, there's a simple polynomial that it does satisfy, so x to the power of p minus p. But the question is that irreducible? Well, yes, it is by Eisenstein's criterion, remember? So Eisenstein's criterion says Okay, let me skip this page. It's going to look a bit messy. But yeah, let me just highlight this. We'll come back to this later. Actually, I'll rewrite it. Okay, so we're trying to show that xp minus p is minimal, by showing it's irreducible. So Eisenstein's criterion, so let's go back to that, says that if we've got a prime such that it divides all of the coefficients except for the first one, but it doesn't divide the first one, and it doesn't divide the last one twice, then f is irreducible. So in this case, yes, we've got p divides p divides 0, all the way up to p divides 0, and then p doesn't divide 1, and then p squared doesn't divide p, okay? So we've shown that all of the coefficients up until x to the power of p minus 1 satisfy this, but it doesn't divide the last one. The first one doesn't divide the last one twice. Okay, so by Eisenstein's criterion, irreducible. Sweet. Okay, so we've looked at that now. Yeah. That means that this is the minimal polynomial of p, the minimal polynomial over here, which means that the degree of this is actually equal to p. So now we have a formula. We have that p is equal to the minimal polynomial of p over p, to theta, times minimal polynomial of theta over q. Okay. The issue is now we know that let's go back down. That means that these two things must multiply to create p, which means that one of them must be equal to 1, the other one must be equal to p. So a good question is, can this possibly be equal to 1, or can it be equal to p? Well, we know it can't be equal to 1 because this thing is not rational, of course. Right? This thing is not rational. Right? Theta is not rational. So that means that this is not equal to 0. Sorry, it's not equal to 1. Therefore, it must be equal to p. And so yeah, we've shown what we need to show. Right, sweet. So we have very little time left, but we'll talk about splitting fields now. So essentially a splitting field, I'll just skip through this slide, you can read through it in your own time. But a splitting field of a polynomial p is an extension field such that we split it into linear factors. Right, so for example, you've got x squared minus 2. This is actually irreducible over q. But if I want to split this thing over linear factors, right, I want to add root 2. So a splitting field, for example, would be q root 2. Okay, that's a splitting field. Okay. There is a formula that says that if we've got f an element of the set of field polynomials, then there does exist a finite extension such that it is a product of linear factors in that field. Okay. That's a formula. And so what you can do is you can generate the splitting field by finding the roots of f, then adjoin it to the field extension. Right, so you've got roots alpha 1, alpha 2, and so on, and you adjoin them one by one. So you go from f, right, to f alpha, and you try to find the field, you construct a tower of extensions, basically. And then you eventually contain all of the roots, and you've got the splitting field. Okay, and you can find, for example, the degree of the extension by looking at the tower of extensions. Okay, we'll probably only do a few more examples, we'll do this example over here. So find the splitting field of the polynomial x cubed minus 1, 11 over q. So it's pretty simple start. Just find the roots. Okay. So we've done this kind of question before. Q minus 11 equals 0. X cubed equals 11, which means that x equals cube root of 11, cube root of 11 times w, or you can just write it as e to the power of I pi on 3. Then this thing. Okay. Let's bring this over. You want to find the splitting field. So it should be 2 pi on 3. But yeah, for example, you want to add them one by one. So you want to basically go from q to q with these 3 roots. So let's construct a tower of extensions. So first of all, let's extend it to the simplest one, so root 3, 11. Okay, so it's fairly simple to show that x cubed minus 11 is the minimal polynomial for that by Eisenstein's criterion. It is irreducible. So because it's irreducible by Eisenstein's criterion, we know that the extension over q is equal to 3. Okay. Then we think about what we do to add this one. Okay. If we add this one, for example, then now we've got we need to find the smallest. Okay, think about this. We need to find the minimal polynomial of e to the I 2 root 2 pi on 3 over this field. And you think about like what we usually do with e to the I 2 root 3 is we know that this satisfies x cubed minus 11. But that's not going to be the minimal polynomial because we can also split this further, right? We've also got e to the minus e to the I 3 times cube root 11 e to the minus e to the I, x minus e to the I. And the last one will just be x minus this. We don't need this over here anymore. But we know that if we combine these 2 roots, we'll get x squared minus, it will actually be it'll be plus this on 2. It'll be that squared. And this actually turns out to be a polynomial with coefficients in cube root of 11. So in other words, if this can be written in this form, then this is the minimal polynomial. So this is actually equal to 2, right? Because we've written it by eliminating the third factor. We've written it as a polynomial with coefficients in the in the field itself, right? So this extension is equal to 2. So that means that we've extended it twice, and it turns out that we've also added in this one, so now this is actually in the polynomial as well. So if you actually write this entire thing out, you've got Q, cube root of 11, e to the minus I 2 pi and 3. On Q, by using the tower of extensions, you've got 3 times 2 equals 6. Okay, and that's going to be your splitting field. You can read out the slides in your own time, but yeah, basically you compute the tower of extensions by looking at the minimal polynomials over each additional element. Okay. Sweet, we'll finish off with one last topic on finite fields. So finite fields are basically fields that have a finite number of elements, and the most common example is if you just have a prime, so prime p, and then you think about zp, or as some people might say, z on p, or z on pz. Basically, this is the set 0 up until p minus 1, where you do modular arithmetic on it. So for example, p minus 1 plus p minus 2 is equal to p minus 3, right? Because we just do it mod p, right? This will be equal to 2p minus 3, which is equivalent to p minus 3 mod 3. So one common example is like the finite field of order 3. It's just 0, 1, 2, and you've got factors like 1 plus 2 equals 0, 2 plus 2 equals 1, and stuff like that. Basically, it's just modular arithmetic. Mod p. Okay? But in general, those aren't the only types of finite fields. You can also have p to the power of n for some integer, right? And then p will be called the characteristic of f. Okay? It turns out that if f is a field with p to the power of n elements, then p actually tells you that it's a cyclic group of order q minus 1 if you exclude 0. If you exclude 0, it's a cyclic group of order q minus 1, right? Because the only element that doesn't have a multiplicative inverse is the 0 element. Okay. Sorry, my bad, sorry. Yeah, that's correct. Right, so you exclude 0 from the group, and then the remaining group, multiplicative group, is a cyclic group of order q minus 1. Okay. So every finite field p with finite field f with characteristic p can be written as isomorphic to the set of polynomials with fp being remember the zp thing that we said before? So 0, 1, down to p minus 1. The set of polynomials with these things as coefficients. Quotiented over the ideal generated by q, where q is a minimal polynomial for some alpha. Okay? And then if the degree of q is n, then the order of f is p to the power of n. Right? So for example, if I have some kind of polynomial like f3x over, I'll just tell you one example, x squared plus 1 is actually a minimal polynomial over fp, then this thing over here is actually isomorphic to f9, because the order of f is going to be 3 to the power of the degree of this polynomial, so 3 squared. Okay. There's an explanation here, but we'll talk about that. We won't talk about that because we don't have time. But yeah, basically, every finite field can be written in this form. You've got fpx quotiented over a minimal polynomial. Okay. Sweet. So we want to prove that these two rings are isomorphic. So they both look to be fields because we've got z on 3z is the field of order 3. And then we're quotienting it over a polynomial. We want to show that they're isomorphic, right? Which means we want to show that they're both fields of the same number of elements. Because It's not written here, but if two fields have the same number of elements, they have the same order. If two fields have the same order, they are isomorphic. Okay. So yeah, let's do this over here. All we need to do is prove that this is a minimal polynomial. If we can prove that these are minimal polynomials, then we've proven that they are both fields. And if we can show that they're the same degree, which they are, x squared, then we'll show that they're both order 3 squared equals 9. Okay. So let's prove that x squared plus x plus 2 is irreducible. How do you do that? Well, we only have 3 elements of this field, so 0, 1, and 2. If you can show that all of them don't satisfy the equation, you can show it can't possibly be split into linear factors. So let's do this over here. 0 squared plus 0 plus 2 equals 2. 1 squared plus 1 plus 2 equals 1, which doesn't equal 0. And then 2 squared plus 2 plus 2 equals 2, which doesn't equal 0. Okay. The whole point is that this can't be reducible. It doesn't have any factors. Therefore, it's irreducible. Alright, do the same thing with the other polynomial. Prove that x squared plus x plus 2 is irreducible. So it's 2x this time. Same thing over here. 0 squared plus 2, 0 plus 2 equals 2. 1 squared plus 2, 1 plus 2 equals 2, not equal to 0. And then 2 squared plus 2 times 2 plus 2 actually equals that'll be equal to 1. It's not equal to 0. So irreducible, and therefore they must both be fields. Both rings must be fields of order 9, and therefore they must be isomorphic. Okay. Sweet. Right. We might skip this question, but basically it's the same kind of thing, right? Each of these things you can kind of try to reduce to a field that's more simple, or a not field, a ring that's more simple, and you can sort them into equivalence classes. They will be on the slides, they will be uploaded to the website very shortly, but yeah, this is that last question. We might finish off with just one question from 2022, just a bit more of an abstract question, that involves some complex numbers, okay? We want to basically show that if alpha plus beta and alpha beta are algebraic over Q, then alpha and beta must also be algebraic over Q. So if we want to think about some kind of relationship between alpha and beta, and alpha and beta, right? Basically, we want to show that if we take the field extension, alpha plus beta, and it's algebraic, that must be finite, okay? So let's think about that. So Q, I'll wait for my pen to charge for just 1 second. Actually, it's charged. Oh yeah. Alpha plus beta, over Q must be finite. Since they are both algebraic, and therefore there must exist a finite polynomial that has it as roots, right? So it must be finite. So then we can construct the tower of extensions, right? We want to think about alpha and beta. What happens if we add alpha and beta to this? Okay. Let's start a new page for this. But basically, that's going to be equal to, we'll do the tower of extensions, but it's going to be equal to the finite number n, so n being this finite number, because we know they're algebraic, times the degree of the minimal polynomial of alpha over alpha plus beta, alpha beta. And we think about, well, we've seen these before in polynomials. For example, x squared minus alpha plus beta, x plus alpha beta, has roots alpha and beta. Okay? So in other words, this is a polynomial that has alpha as a root. So in other words, this must be less than or equal to, well, this will be that multiplied by the degree of the extension of this over alpha plus beta, alpha beta, which as we've established is less than or equal to 2, right? So less than or equal to 2n, okay? So that's this first one. Then we add beta to it. And again, this extension yeah, so if you add beta to it, it's the same kind of idea. Like beta is a root of x squared minus alpha plus beta x plus alpha beta, which means that this is going to be less than or equal to 2, because we've already found one polynomial with degree 2 that satisfies this. So what that means is that this entire extension is less than or equal to 4n, okay? Which then means that we have that alpha and beta must be the roots of finite polynomials over Q. So they must be algebraic, since the extension is finite. Alright, that's one final question that we can do to kind of test our more abstract thinking. But yeah, that's a complete run through of the 3711 course. If you have any questions, just put them in the chat. But yeah, that's a pretty comprehensive summary of everything we'll need to know for rings and fields. So yeah, good luck for your finals, all of your finals, not just 3711, whatever other finals you might have. And hopefully you found these two seminars useful. And yeah, thanks for tuning in, and I'll stay online for a few minutes just to, if anyone has any questions, but thanks for coming. All right.